That's okay. Let me introduce myself first. My name is Chia-che. I'm a junior faculty at Texas A&M University. I'm also from a project called Graphene Library Open System. And also, actually, interestingly, I was a postdoc here in Berkeley last year and working in Rice Lab. So the kind of project I usually work on is the operating system support and language runtime support for SGXs. But I think there's a lot of very interesting challenges not specific to SGX, and I want to basically talk about these sort of generic theme of these challenges today. All right, finally it's up. Right. So the kind of problem like we usually run into of trying to provide any kind of OS support or language runtime support is basically how to partition the system software. And this is a kind of interesting problems, and actually a very ancient problem, I would say, actually. And the reason why this is so important is if you look at how Enclave usually work, right? So imagine you have some kind of application, and that application is a target of your Enclave protection. You want to protect that with your hardware, right? And that means like in order to make that application works, you might have to rely on some kind of the language runtime support, or library supports, or operating system support, right? And so the kind of question is, why couldn't we just sort of go with kind of virtualization system, basically put them all into Enclave and basically call it a day, right? We don't have to do partition at all. Why wouldn't that be the case? Well, in fact, a lot of time you do have to talk to I/O devices, and these I/O devices obviously less trustworthy. Usually they have vulnerability, it's much easier to attack them. There's a lot of attack being seen recently. For memory, you have Cobra attack, you had Rowhammer attack. For regular PCIe, you see a lot of many in the middle attack. And these things cannot be fully trusted. Oh, sorry. All right, so that means, well, you basically had a problem where in the application, that's sort of the source of your secret that come from. And you got the I/O devices is basically a sink where you will worry about if data get leaks over there. So this has actually become a sort of classic data flow tracking problem, basically. And this is not only data flow in the data plane, but also data flow in the control plane as well. So that's make it really complicated. And so the kind of question here is, well, now in order to solve this problem, we basically have to sort of draw a line in the middle and say, okay, this is the places we're gonna put into Enclave. And outside Enclave is maybe the operating systems or the library, wherever you want to draw the lines. And so the question is, where is this partition boundary supposed to be? And how do you declassify the data when you cross this partition boundary? And this has become a very challenging problem. And so how do we solve this problem? Well, there's actually a lot of work trying to address this problem. And usually they sort of fixated on two concepts. One is called attack surface, and another one is called trust computing base. And the people constantly debate about these two concepts. Right? So for example, there's one cases where you have very large attack surface and a small TCP. So basically you have a system IP on top, and you try to have some kind of redirection layer. Of course, you need to try to defend this layer and basically jump out Enclave immediately and try to talk to the untrusted operating system. This is called a shim layer approach. For example, for SGX, you might have heard this word called scone. Basically, they are going with this approach. There's another approach where you have small attack surface, but you have a large trust computing base. So you got a guest operating system sitting inside Enclave, and you kind of cut it in half and basically export some kind of hypervisor interfaces. And in this case, it's usually called a library OS approach or unikernel approach. So case in point, the project I was working on, Graphene and SGX LKL, this kind of system is basically based on these kind of ideas. Well, so the kind of question is, how do we think about this problem? Like, is attack surface matter or TCP matter? And I kind of feel like the answer is none of these are really what's getting the point. It's both kind of elusive because none of them really capture what is the problem we're running into when we're dealing with operating system support inside Enclave, right? And so really the kind of problem is we need to know what's going on when you partition an application, when you expose the interfaces when you're inside your system, what happened to it. And this kind of problem usually, there's a classic problem we usually said, it's called, basically if you have an application, they try to use some kind of legacy system API, for them try to get a PID or try to get time of day. When you talk to an untrusted operating system, that means the operating system get to do whatever they want. They can return any kind of malicious result back to the legacy application and basically manipulate the execution to basically to expose their vulnerabilities. And this is a classic problem, what we usually call Iago attack. And so if I heard of an Iago attack, basically this is a situation where a trusted operating system can exploit semantic vulnerability inside applications that is misplaced. Basically, it was mistrusting these API. They thought these API is trustworthy, but now it's not. So this become a problem. For example, if the PID and time is actually controlled by the output system, I mean, it's not a reliable source of entropy. But you do see some application, they try to use time and PID as source of entropy. And if that happens, that becomes a system vulnerability. And this is just a very classic example, but not the only example. If you see, this has become a sort of pervasive threat inside, not just inside operating system, but also in library. So a lot of library, for the POSIX interfaces, they basically trust the POSIX interfaces and trust the result of the POSIX interface. Or the runtime, we actually see this situation in the language runtime. If you sort of trust these classes or method interfaces and you sort of just pass some kind of value in, they might sort of just exploit that thing, especially if this interface is polymorphic. That's even more, make it even more dangerous. And even hypervisor could potentially have this interface problem as well. And this is integral to the design of the system. So how do we think about this problem? Because this is sort of at the beginning when we try to pour some application or pour some system into Enclave, this is what's going to happen. So this is, I actually want to say, this is the right way of solving this problem is thinking about how to design a secure interface from the beginning. And so usually I would draw a line. This is the secure host interface you can put there. And you can think about different kind of secure abstraction that you can actually pull from your system. For example, you have secure boots. You can start process that right correctly. But secure clock, you want to have usually you want to have two clock. One is a monotonic clock that is have higher precision but less accurate. And you have a day clock or wall clock that's have lower precision but is more accurate. You can have secure virtual virtual memory management for stack and heap, secure I/O, secure RPC, and sometimes you do need secure scheduling. But when you talk about this is kind of no man's land because this is really difficult to do because you need to have full control of the CPU right now. So this is when this happens, you can potentially have a denial of service happening. But if you have all these things, that's all you need, then you can use this to get legacy system API secure. For example, if you have secure boot plus secure virtual memory plus secure RPC, you can do fork. Or if you do secure I/O plus secure RPC, you could do any kind of IPC implementation, for example, message queue, semaphore, signal, or file logs. Or if you combine secure I/O with secure scheduling, you can do asynchronous I/O. So this is just an exercise. You can combine all these different things to emulate the traditional system API and get what you want to support the Linux applications properly. And so based on this spirit, we actually create this project called Graphene. So Graphene is actually open source project that is meant to build a library operating system to support a modified Linux application for Enclave. And we want to do it secure, with a secure interfaces. And so that's why we have an open source work group. So it's basically this group across several institutions, including Intel, including Golem, and Invisible Think Lab. They are the startup companies that's working on building secure platform, and academy, including UNC and Texas A&M. So we're working on building these things. And so for Graphene, we actually was able to sort of build a huge system stack, including a lot of features that application are need for one of the Linux platform. And on top of this, basically, we can build on top of what we call a Graphene host API. API is small, it's simple, it's portable, and it's highly secure. And so it's designed with secure semantics in mind. So based on this, we can port it to SGX, and we have ported to SGX and create a shell for it. But I don't think SGX is the only thing they should be ported to because this is designed to be portable. It could be ported to potentially in the future any kind of hardware enclave. That's all possible. It also is not just designed for enclave; it could be treated as a containerization solutions, or a non-Linux platform port is all possible. We have implemented 140 system calls so far. Have 63,000 line of codes and 1.4 megabytes library size. So this is the graphing project. We're basically pushing a stable release right now, and if you're interested, you can try it out. All right. So we don't have enough time, but let me quickly jump to another work I was doing done. Is we actually see not just the operating system needs to be partitioned, but also language runtime needs to be partitioned. So if you think about language runtime, it actually crosses several layers. If from the application itself to language runtime to library, ideally you want to just carve out a huge, nice chunk of system stack from the existing system stack to do what you want in a minimum security requirement. But this is actually really hard if you think of something that's really big, like a Hadoop application. There's so many codes. There's so many codes in there, and if you want to either manually try to or automatically partitioning it, it's all very hard. So we actually propose a solution, what we call Civet. This is the collaboration with Raluca and John Salk. They are both from Berkeley, and Don Porter and Bhushan Jang, they're both from UNC. We're basically designing a solution that's based on language techniques and language static analysis tools to basically, you can take applications and partitioning into two parts. And this is not just partitioning in the application level, but also including partition necessary for the language runtime part. And so you basically had a whole system stack, cross-stack partitioning being packed into that trusted jar. And during runtime, you can basically easily launch them. You'll have interface classes where they can basically plug into existing Hadoop framework and just run these mapper and reducer, any kind of partition entity you want, put into Enclave. And it will have defenses for it, and we'll have a partition JVM sitting there. Okay. So since we don't have time, let me jump to last conclusion. So my conclusion here is the system partitioning is actually really critical challenges, and it's usually omitted in the world of hardware enclave. And so I want to say, for the OS run level, we're basically working on this work called graphing libraries. Our idea is to emulate legacy system API like Linux system call on minimum secure abstractions. With runtime level, we are working on this work called Civet frameworks. Eventually, this is not open source yet, but we're working on open sourcing it eventually. And this is working on a static cross-stack partition solution just for Java applications. And it needs to have all the kind of language defenses and optimization to make sure it is suitable for production use. And so this is the whole ideas. If you have any questions, do you have time for questions? No.
I think
that's
we're
okay.
running short of time.
Then we can, if you have any questions, feel free to find me later.
So yeah.